Hello, my name is Rosario Hanon and this is my lab report about the motion of falling objects. Throughout this lab, we'll be analyzing the motion of falling objects and the different forces that interact with them. In this case, the force of gravity and the force of drag. First, I got two different objects, one falling rapidly and another slowly, and I analyzed them in the tracker. The first object, the one that's falling rapidly, is illustrated in this video where I set the coordinate axis and then I measured the diameter and tracked them by using a point mass marker. So we start and we play it, and I got this nice parabola-like graph. I put it into Excel, and after that I got the graph and the information. That is in this table. I inputted the mass in Python, and I got 0.04, the velocity initial, the initial position, which is in here, in the experiment, and the time step. The force of gravity was added. It was negative 9.8 newtons for the first one. I ran the code and I got a graph that will be shown in the next slide. And then I did another one including drag, and our constant B was 0.018. As you can see, here are our information gotten from the models. And the force of drag is negative B times ball dot velocity, which is stated in the prompt. And here's our graph number 1, which you can see the experiment is the orange square, and the model with drag is it's barely visible because it's really like when the experiment is marked is the red diamond, and then the model of gravity is the green triangle. So you can see that the model with the drag and the experiment are very, very similar, because we're taking into account the two forces that interact in real life. And the model of gravity is sort of similar, since it's an object that drops rapidly, and the force, and sometimes, in this case, sometimes drag is overlooked. And then we moved on to our second object, which is a paper tower ball. Here is our video, also with the coordinate plane set, the diameter, and the tracker, the mass point. Here's how it's analyzed, and here it's how it's plotted. It's still parabolic, but a lot less than our fast moving object. So we also took the data and plotted out in Excel and also in our PowerPoint. It's right here. So here's the data we got from the experiment with gravity only and only the drag. So mass again 0.01, it's less, velocity initial 0, the position, and the time step. And the force of gravity is negative 9.8, as we discussed earlier. And the drag included, with the drag included, you add our constant, in this case was 0.0254. And our force of drag was negative B times the velocity, which is a given. So we put everything in our code, and after that we got this data, right? And we plotted this in Excel in a chart, and we got a huge difference this time between the gravity, the force of gravity only acting on the ball, and the force of both the drag and the gravity. Here is how it's very similar again to the experiment, and there's a huge difference between the experiment and the drag, the experiment and the gravity, and the drag and the gravity, as you can see in this chart. Now we're gonna, why is this? Because the drag, it's larger since the ball drops slower. And then for the question, for the object that drops slowly, examine the velocity versus time predicted by your model, with and without drag. Which model, if any, predicts the terminal velocity? Discuss briefly. So the models with drag, especially one in which the drag is significant. So this case, the object that drops slowly. Because as the force of drag increases and starts equaling the force of gravity, it starts totaling a net force of 0. Thus, there's 0 acceleration and constant velocity, which is a terminal velocity. So you have drag and it's increasing because velocity is increasing. And then you have the force of gravity, which in this case is constant. So drag gets bigger and bigger each time. And you have the velocity, and the forces equal together, making a net force of 0. Then for the next question we have, for the object that drops slowly, use your models to examine the object's velocity as a function of time. In this case, where the object is thrown downward initially, and also in this case, does the object reach a terminal velocity? Compare the terminal velocities in this case with the case where the object is dropped from rest. So we have, in the case of gravity only, from rest the final velocity, it's 6.90184, and when the initial velocity in the model, I input negative 1 meters per second, and it gave me negative 7.59232. So in the case of gravity only, it starts getting to the point where the velocity starting to get constant. In this line, as you can see, it's starting to get, like, the slope is starting to be very constant. And in the case of initial velocity with negative 1 meter per second, same thing, but it starts a lot earlier. So see, like, the slope starts being constant since a point further up. And now again, with our case with the drag included, we have from rest negative 1.15791, and with initial velocity of negative 1, our final velocity is negative 1.15852. And here, like, the difference is a lot bigger, because you can see, like, this is slightly parabolic and then starts and becomes constant. But this looks like it's constant all the way, and it only changes 0.15 seconds. Thank you so much. This was my lab.